Before we start with this video, I would like us to go through a number of concepts. Let us consider a number line. The number line starts from minus infinity to positive infinity, and in it we have a minus 1, a 0, and a 1. Let us say the domain of this number line is R, of which R is the constant ratio of a geometric series. In this number line, we will choose a number between minus infinity and minus 1, so that will be minus 2. A number between minus 1 and 0, and that will be minus 1 over 5. A number between 0 and 1, and that will be a half. We're just choosing any number. A number between 1 and infinity, that would be 3. Let us consider the formula, or the general formula of a geometric series, which is ATN equals A times R to the power n minus 1. Now let A be equals 1, and let us evaluate the sequence per term of the geometric series given by the constant ratios that we have chosen on the number line. So we have Tn equals, our A is 1 and our first constant ratio is minus 2 to the power n minus 1 equals, so that will give us a sequence as follows. So our first term will be equals 1, our second term will be minus 2, third term is 4, positive 4, and our fourth term will be minus 8, and our fifth term will be 16. We will only consider 5 terms for each. For the second constant ratio, we have Tn equals A, which is 1, and our constant ratio is minus 1 over 5. The n minus 1 equals, our first term will be 1, our second term will be minus 1 over 5, the third term will be 1 over 25, fourth term will be minus 1 over 125, and our fifth term will be 1 over 625. Now let us consider for the third constant ratio. So we have Tn equals 1. Our third constant ratio is 1 over 2. One over 2 to the power n minus 1. So our first term is 1, the second term is 1 over 2, and the third term is 1 over 4. The fifth term is 1 over 8, and that was the fourth term. Our fifth term is 1 over 16. Let us now consider our fourth common ratio, So we have Tn equals 1 into 3 to the power n minus 1. That's equals, the first term is 1, second term is 3, 9, 27, and 81. Now let A be equals 10. We will choose one of the sequences that we have considered, and we will choose the sequence with the common ratio of -2, and for it we will change the value of A from 1 to 10. So we have Tn equals 10 into -2 to the n minus 1. So what will be our first term? So our first term is going to be positive 10. The second term will be minus 20. The third term will be 40, and the fourth term will be minus 80, and the fifth term will be 160. So let us plot these sequences in the same plane. Our plane will not be of scale. We will just plot these not considering the scale. So let us start with the first one. So our range will be Tn, or our y-axis will be Tn, and our x-axis or our domain will be n. So we have n equals 1, n equals 2, if n equals 3, n equals 4, and we have n equals 5. Plotting our values. So for n equals 1, we have 1 on our first sequence. For n equals 2, we have -2. For n equals 3, we have 4. For n equals 4, we have 8 or -8. For n equals 5, we have +6. 16, somewhere there. So let us join these. So we can notice that when R is or when the common ratio is negative and a whole number, we can notice that our sequence alternates, and we can say that the sequence diverges, as we can see that the sequence is simply increasing in both positive and negative of the of Tn, or the range of the y-axis, without stopping. So let's write this down. So for Tn equals 1 minus 2 n minus 1, our sequence alternates and diverges. Now let us plot for R equals minus 1 over 5. So for R equals minus 1 over 5, our first term is 1. The second term is minus 1 over 5. So we can say that is minus 1 over 5. And the other one is positive 125. There's our positive 125. And we have 1 over 25. And the other one is negative 1 over 125. So sum here. And our last one is 1 over 625. Somewhere there. So let us join these as well. So for this one, we can see that it the sequence alternates, but however it reduces as n goes to infinity, or as n increases, and this is called convergence. So for Tn equals 1 into minus 1 over 5 n minus 1, our sequence alternates and converges. Now let us look at Tn is 1 over 2. So our first term is 1. So there is 1. Our second term is 1 over 5. 1 over 2, sorry. Our third term, sorry, that's incorrect, is 1 over 2. 1 over 2, sum here. Our third term is 1 over 4. Somewhere here. Our fourth term is 1 over 8. And our fifth term is 1 over 16. So if we join this, So we can see from this graph that the graph doesn't alternate, but however it only converges, or it goes or tends to 0 as n goes to infinity. So for Tn equals 1 into positive 1 over 2 n minus 1, our graph converges. Now let us look at the graph of constant ratio 3. So our first term is 1. There is 1. Our second term is 3. Our third term is 9. Our fourth term is 27. Our fifth term is 81. So this graph somewhere, it's not a straight line, it's exponential. It's just that this is not drawn to scale. So for Tn equals 1 and r is 3 to the n minus 1, you can see that our graph or the sequence diverges, or it goes as n goes to infinity. It doesn't settle to any it doesn't seem to tend to any specific number. Now let us look at the graph of Tn equals 10 and constant ratio of minus 2. So our first term here, our first term is 10. So there's our 10. And our second term is minus 20. There's minus 20. Our third term is 40. Our fourth term is minus 80. And our fifth term is 160. So 160 could be somewhere there. So let us join. So for Tn equals 10 into minus 2 and minus 1. So we can see that the sequence alternates and diverges. But however, we can notice, what we can also notice from this sequence is that it is similar to this one, and the only difference is that the sequence has values that are 10 times larger than for when a equals 1. So we can say that the effect of changing the value of a will change the will only change how big the values are in the sequence, or we can say it changes the amplitude, or the amplitude of the sequence. And the amplitude is the length at which the sequence or is the length from 0 to the first to the highest point in a sequence, or in a graphical or a graph representation. So we can see here that there is a difference. There is a difference in amplitudes. That is the only difference, but the graphs are the same. You can see here. So the graphs are the same, but there is only a difference in amplitudes. So we can conclude that and therefore we can conclude that A, whose also the first term also affects the amplitude of a sequence. And now let's come back to the number line. So what can we say about the numbers or the constant ratio between minus infinity and minus 1? So we've already seen that the sequence in this region will alternate and diverge. And in this region, the sequence will alternate and converge. And in this region, the sequence stays positive or stays above the zero line, and it only converges. And from here to positive infinity, the sequence diverges. So we can go ahead and conclude that convergence occurs between minus 1 and 1, or when r is between minus 1 and 1. Anywhere else, but however, let's not forget that r must not be equal 1. And also anywhere else in the in the number line, the sequence will diverge. So how can we explain convergence? So convergence can be explained in two ways, and this is only the first way of explaining it. So convergence occurs when the constant ratio is between -1 and 1. So if the constant ratio is a fraction, the sequence will converge. And we can see that in a converging sequence, as n goes to infinity, the sequence will tend to a certain number. And as we have seen in our graph here, it tends to 0. However, it may tend to any number. The second way of explaining convergence is by looking at the sum of the sum to infinity of sequences. Let us calculate the sum to infinity for the sequence that has the constant ratio of 1/2. So the sum to infinity equals a over 1 minus r. So that is our a for this sequence was 1. So we have 1 over 1 minus 1/2, and that will give us a sum of 2. Let us calculate the sum to infinity for the sequence that is a constant ratio of -2. So the constant ratio of -2. So sum to infinity equals a over 1 minus r, and that is 1 over 1 minus into -2, and the answer here will be 1/3. So we can also calculate the sum to infinity for this sequence, for the sequence where our constant ratio is 1/2. But however, let's change the a to the value 10. So we have 10 over 1 minus into 1/2. So the sum is 20. So we have already seen that for this for the sequence with the constant ratio of 1/2, we get convergence, and for this one we get divergence and convergence. So the sum to infinity is 2, and we can see this because we're starting from 1, and then we're adding smaller numbers as we go to infinity. So we can add as many numbers as we like to infinity, the sum of this series will always be, or the sum to infinity will always be equal to 2. But however, on a diverging series, the sum to infinity is a number that doesn't make sense. It should be a very large number, as we can see that diverging sequences tend to increase in either the positive or the negative or alternate, but however they tend to increase, so a larger number can be expected for their sum. So how this does not make sense. So this is the second way of explaining convergence. The sum to infinity of a converging sequence will converge to a certain number, but the sum to infinity of a diverging sequence, it does not make sense. So we will end there, and those are some of the concept of a geometric series or sequence, of which is convergence and divergence, and one must keep these in mind when dealing with geometric sequences. So we will look at some problems of geometric sequences and series.